So thank you very much for joining us today for another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Communications Director and Director of Legislative Affairs here with LIFT. Thank you very much for taking some time to join us today. We are excited to hear from CompuTherm and their new generation of simulation tools for ICME applications, which is very important to LIFT and the industry going forward. So a few housekeeping items before we get started. First of all, hopefully everyone is safe and well as we hopefully are turning the corner out of this 15 months of pandemic time and slowly getting back to normal. But hopefully everyone is still taking precautions and being safe, as safe as they can be. A few housekeeping items with the webinar before we get going. This session is being recorded, so if you can put your phones and computers on mute, that would eliminate any background noise. And we won't have it for the recording. That will be posted on our website at lift.technology later on today, and you'll be able to share it with folks who were unable to attend, or if you'd like to revisit it to catch anything you may have missed, you can certainly do it that way with the Liftoff replay that will be posted later. We will have a Q&A session at the end of the presentation today, so please use the Q&A function that is on the toolbar of the Zoom platform here. We know everyone has been operating on Zoom or Teams or other platforms, so we all know how to use the Q&A. So please go ahead and submit your questions throughout the presentation, and we will facilitate that Q&A afterwards. In the meantime, sit back and relax, and we will get going. I do want to share a little bit of information about LIFT for those who may not know who we are and what we do. We are one of 16 national manufacturing and innovation institutes from around the country. 9 of the institutes were sponsored by the Department of Defense, and LIFT is one of those. Our goal is to drive American manufacturing into the future through technology and talent development. So we believe that American leadership resides in smarter manufacturing. We believe that our economic security and resiliency resides in smarter manufacturing. And so that is what we are driving towards. Now, what do we mean by smarter manufacturing? At LIFT, we mean that that is the connection between materials, processes, systems, and talent. Looking at the manufacturing sector holistically, not just looking at materials, not just looking at processes, but understanding how those all work together to move the needle as it relates to manufacturing innovation and taking innovations from concept and initial prototyping across the valley of death and into production for the manufacturing industry and into the hands of the warfighter as we're dealing with the Department of Defense. So we do this through 2 programs at LIFT. The first is our Leading Innovations for Tomorrow program. That is our technology program. And second is our Learning Innovations for Tomorrow, which is our talent program. So a little bit about both of those. You can see on the screen, Leading Innovations for Tomorrow. This is our technology program and the 4 pillars of technologies that we focus on. And you can see the very first one is Integrated Computational Materials Engineering, which we will hear from CompuTherm about later on during this presentation. But we also focus on agile and smarter manufacturing, back into our history and materials with advanced alloy and process development, as well as multi-material joining. A little bit deeper dive into each of these on the screen now. I won't quiz you on these, but just give you a little bit of the breadth and depth of our technology program and how we operate with each of those technologies. Again, the goal is to take technologies that is being innovated, being researched, being developed, and moving that across the valley of death to really advance them so we can move advanced manufacturing forward here in the United States of America. On the talent side of the equation, we also are focused on innovation, and that is really on new learning tools, pathways, and venues. And we really like to highlight our Ignite Mastering Manufacturing curriculum. That is our curriculum that was developed with funding from the Department of Defense to open up the eyes of high school students, mostly, to the world of advanced manufacturing, give them some hands-on experience, give them some virtual online experience, and that takes place at the LIFT Learning Lab. Pre-pandemic, we had 120 students at any given time in our facility, participating in our hands-on and virtual experiences to really, again, open their eyes to what the world of advanced manufacturing looks like here in 2021. And we're looking forward to having students back in the learning lab in the fall when school resumes. We do have students in the learning lab, however, participating in our world-class certification programs, both our certification programs as well as a program called Operation Next. So we offer certification classes in CNC operations and welding. Also through Operation Next, we offer CNC, welding, industrial technology, maintenance, and robotics. Operation Next, it started as a program for the military, separating men and women from the service. We're getting ready to leave their 4 years or 5 years, whatever it was that they served. We wanted to give them the opportunity to earn credentials in some of the most in-demand advanced manufacturing jobs. So when they left the service, they had those credentials in hand and were able to find a job immediately. So it was successful. That program is growing across the country. We paired that with our LIFT certified certification program. So we are running courses through our facility as we speak. We've also piloted Operation Next into industry. So in Detroit and Pittsburgh, we are working to help small and medium-sized manufacturers get off the mat, if you will, from the pandemic and get some folks trained and ready to take these advanced manufacturing jobs that are available today. We've all heard about the manufacturing skills gap that exists, and we are here to help solve that issue. So I mentioned that we are supported by the Department of Defense, one of the National Manufacturing Innovation Institutes. We are a public-private partnership between the Department of Defense, industry, and academia. We are a nonprofit 501c3 based here in Detroit. So to become a member, what does that look like for you? What does that mean? Well, it means that you get the opportunity to receive all of the benefits that are on the screen here. We are a trusted advisor, really advising small to medium-sized companies mostly on how to make that change to smarter manufacturing. We know that we work with a lot of large companies as well. They are already moving down the tracks as it relates to smarter manufacturing. We want to make sure that the small and medium-sized companies can play in that space as well and keep up with their large customers. Technology Accelerator, we spoke about that already, really transitioning innovations from research and development into commercialization. A technology Showcase, our facility in Detroit handled 5,000 visitors a year pre-pandemic. We really look forward to having you visit us in Detroit when it is safe and you're able to do so to really show you the art of the possible when we connect materials, processes, and systems. So please reach out to us and we'd be happy to host you. Connector and convener, that's why we're all here today. So thank you very much again for joining us today. We really want to bring the top minds across industry, academia, and government together to, again, move the needle with advanced manufacturing. Talent developer, we spoke about this a little bit earlier, but really making sure that the manufacturing workforce of the future has the knowledge, skills, and abilities to work with and succeed with these innovations and processes that we're currently working on. And finally, we are a government partner. Government, the federal government especially, can be a large bureaucratic operation to work with really no easy entry points. And we want to be that easy entry point for you. We have a number of contracts that we work with the federal government, directed projects and other opportunities. So please reach out to us. We'd be happy to speak with you about working with LIFT, becoming a member, and how we can help you succeed. So you can see our contact information on the screen. You follow us on LinkedIn, follow us on Twitter, reach out to us on the phone like olden times, or you can email us or visit us on the website as well with more information. But that is LIFT in a nutshell. I do want to turn the presentation over to Fan from CompuTherm to speak about her ICME tools and new generations of them going forward. So I'm going to stop sharing my screen and hand it over to Fan. So the show is yours.
Thank you, Jill. Let me share my screen. Can you see my screen okay?
Yep, we can now. Thank you so much.
Okay. All right. Hello, everyone. Good morning, good afternoon, depending where you are. Thank you for attending this webinar, and thank you, Jill, for the introduction about LIFT and also about us. And also give us this opportunity to talk about CARFAT method and simulation tools developed by this method. We are a member of LIFT, and yeah, I encourage every one of you to join LIFT as a member. So join the membership and be smart in manufacturing, right? Okay, so today I'm going to talk about a new generation of CARFAT simulation tool for ICME applications. I'm Fan Zhang from CompuTherm. If you have never heard about us, here is a little bit background about the company. CompuTherm is a spin-off company from University of Wisconsin-Madison. It was founded by Professor Austin Chen in 1996. Our mission is to develop intelligent, reliable, user-friendly computational tools for application in the field of material science and engineering. We have been working on many government projects, and we also collaborate with industry companies and institutions working on challenge programs. We located at Madison, Wisconsin, and here you see a beautiful glass building. This is not our office building. We are not that rich yet. Okay, this is Wisconsin Trade Center, but we have an office suite in this building. So in the future, if you have a chance to visit Madison area, you are welcome to visit us. Okay, our major product at CompuTherm basically include Pandex software and a variety of databases for materials simulation. So the database including like thermodynamic databases, mobility databases, and like more volume databases, and so on and so forth. And these databases cover various of alloy systems such as aluminum alloys, nickel alloys, titanium alloys, and so on. And our goal is to use the simulation tool for accelerated material designs and development, and also provide solutions for industry applications. Okay. Here is the outline of my presentation. First, I will use a few slides to talk about CARFAT method, very brief introduction about this method, and also about ICME. And then I'll talk about Pandex software we developed at CompuTherm, its history, like basically from first generation to the third generation right now. And then I'll spend some time talking about the software which has been extended to microstructure modeling, and then summary, okay? So I would like to use this one slide to summarize what CARFAT method is. Well, actually the name is an abbreviation of calculation of phase diagram. So at the very beginning, the approach is really to use available experimental determined data and also theoretically calculated data to obtain self-consistent Gibbs energy functions of phases in a system. This process, we call it build a thermodynamic database. And then the purpose is really to predict stable and metastable phase equilibrium and the thermodynamic properties in the composition regions where experimental data are not available, especially in the multi-component systems. So I know nowadays everybody is talking about machine learning, right? But I wouldn't say CARFAT method is a machine learning approach, but there are some similarities. Basically, in both methods, we use available data to build models and obtain model parameters. And then we use those models and the parameters to predict properties that are not known experimentally. So that's very similar in both approach. Machine learning is a new concept. So, but CARFAT has been here for about 60 years. It's really started in the early 1960s. Every year we have a CARFAT conference at different countries. And this year is in the United States, but unfortunately we cannot do it in person. So we'll have online meeting this year. Actually, it's going on in June. If you are interested, send me an email. I will let you know how to join the meeting. Okay. So as I said, CARFAT represent calculation of phase diagram. So traditionally, phase diagrams were measured experimentally. However, this method is viable for binaries and ternary system. When you go to multi-component system, it's really not viable anymore. So, but however, modern material design is usually based on multi-component system. So the initial idea of CARFAT method is to calculate live and multi-component phase diagram, something like such like this phase diagram. If you compare this calculated multi-component phase diagram, is quite different from the binary phase diagram, which you usually see in the handbook, right? So basically, multi-component system can be very complicated, okay? So the first generation software mostly focus on phase diagram and thermodynamic property calculation. For example, we can do like binary and ternary phase diagrams, right? And multi-component phase diagrams. And we can even do other calculation like point, line calculation, thermodynamic properties. And we can also even do some like solidification simulation using level rule and shell simulation. So that's first generation software. And then after a few decades of development, CARFAT method has really gone beyond phase diagrams. So the second generation software are usually featured with integration of thermodynamic calculation with kinetic simulation. Some of the kinetic simulation include like solidification simulation, like this one shows, and you can consider back diffusion in the solid and cooling rate and so on and so forth. And diffusion simulation, like in the diffusion couple, you want to see how the element diffusion to each other. And then precipitation simulation and so on. And for this type of simulation, direct coupling of kinetic simulation with thermodynamic calculation is possible since only limited number of calls are needed during the simulation, okay? So CARFAT simulation tools are really important in ICME because with this type of simulation tools, we can optimize the alloy chemistry and processing condition, so we can develop microstructure that's are good for the properties and the performance. So this is what CARFAT, the purpose of CARFAT simulation tools, okay? So with this goal in mind, we have developed Pandex software, and this software has evolved from the very first generation only for phase diagram and thermodynamic property calculation, and to second generation, which we can do solidification, diffusion, and precipitation simulation. And now we have evolved to a third generation, which can do like a phase field simulation. And then I'll talk about that one by one in this presentation, but very briefly. So this is the design of Pandex software. I can call it an integrated modeling platform, or you can call it like a software suite and so on. So it doesn't matter what you call it, basically it adopts a modular design. So in this design, we have different modules, right? And this design allows us to continually extend the software capability by adding more and more modules. So phase diagram module is for thermodynamic and phase diagram calculation. Pan optimizer is for optimization of model parameters. These two modules belong to the first generation of software module. And then pan precipitation is for precipitation simulation, pan diffusion for diffusion simulation, and the solidification simulation. These three modules belong to the second generation software. And this phase field module is belong to a third generation. Okay, so next I'm going to use a few examples to demonstrate what we can do with the software, right, with each module. So as I said, first generation pan phase diagram module, which really focus on phase diagram calculation and thermodynamic property calculation. But one unique feature I want to mention here is high throughput calculation. What do I mean by high throughput calculation? Well, let me use an example to demonstrate. So if you work on nickel-based superalloy, 718 is a very popular alloy. And as we know, commercial alloys usually have a spec range. Here in this table, it lists the composition range of 718 alloys, right? So as you can see, nickel can vary its composition from 50% to 55%, and then chromium from 17 to 21%, and so on and so forth. And alumina is a very small amount from 0.2 to 0.8%. So many people would think, okay, this small variation will not do anything, right? But actually, this is not true, okay? We can find out that this small variation of alumina will play an important role in the microstructure development. So with a high throughput calculation, we can perform massive calculations in the composition range, in the composition space. And then we allow the composition of each element varies in the spec range, okay? For example, here, I just show you how we can set up a high throughput calculation. In this case, alumina can vary from 0.2 to 0.8%. And then I give 6 steps. Basically, you can vary it from 0.2, 0.3, and 0.4 all the way to 0.8, all right? And chromium from 17 to 21%, I give 8 steps. And so on and so forth for all the other elements. Here, iron is the balanced elements. So in other words, while I give the other elements, the composition is fixed, then iron will take the rest of the amount, so it makes 100%, all right? And I can change the temperature. For example, I change it from 600 to 800 degrees centigrade, and then I give 10 steps. So with this setting, a total of 480,000 calculations will be performed all together with this simple setting. And then the simulation results can be analyzed according to user's will, okay? So you define what you want. And then the software will perform automatic analysis of the data, and then the analyzed data will be presented as a table or plot, all right? So here I just use, in this slide, I'll use 2 example plots. The left figure is a fraction of gamma prime phase as a function of niobium composition and alumina composition. So as you can see, alumina varies from 0.2 to 0.8%. The volume fraction of gamma prime can vary from 2% all the way to 14%. And then the right figure is the fraction of gamma double prime. And as you can see, the the gamma double prime take the opposite trend. So when you increase alumina content from 0.2 to 0.8%, the volume fraction decreased from 19% to 12%. So as you can see, through high throughput calculation, we can quickly understand the effect of each alloy element in its spec range. Therefore, the alloy composition can be optimized depending your needs, all right? So I use just one quick example to demonstrate how we can use pan-phase diagram module to optimize the alloy composition. And in the next few slides, I want to talk about the other modules, the second generation module, like for precipitation simulation, diffusion simulation, and solidification simulation, okay? So this is an example for precipitation simulation. In this example, we do a simulation for alumina alloy, a ternary alumina alloy, and the left figure shows the particle size evolution as time, and the right figure is the yield strength evolution with time. As you can see, the particle size increase with time continuously, while the yield strength reach its peak value and then it decreases, which represent over aging, right? So this is so with this type of calculation, simulation, we can perform virtual experiments. So in this slide, I show virtual experiments. We basically perform aging at 4 different temperatures. As you can see, at higher temperature, then you can reach a peak yield strength very quickly. However, it's not the best, it's not the highest yield strength, right? And then you can use other temperatures. So with this virtual experiments, you can select the best aging temperature and for your to reach the highest yield strength with the shortest time. And the red figure basically we show the alloy composition can also affect the yield strength. So with this type of virtual experiments, we can optimize the heat treatment condition and also alloy composition, right? Diffusion module, we can do, is used to understand diffusion kinetics, such as elemental diffusion. And in this case, this is diffusion between Inconel 100 and alloy 718. Both are multi-component system. As you can see, we can simulate how the element diffuse into each other. And we can also do like diffusion in diffusion sandwich, like the right figure shows, okay? And one good application with pan diffusion module is the carbonization simulation. So in this figure, we can simulate how carbon from the environment diffuse into the steel matrix. So this is early stage last time, and this is a later stage. So it's clear demonstrate how carbon can diffuse into the substrate. Of course, you can define different boundary conditions, such as you can fix the carbon activity, or you can fix the flux of carbon, right? And with a diffusion module, we can also do like a homogenization simulation. In this case, we simulate how the alumina copper particles dissolve in the alumina matrix. So this is the particle size, y-axis, and this is the time. So at the beginning, we have a very big particles, and then gradually it will dissolve with time. Okay. So for the third module for second generation software is basically pan solidification. Pan solidification module focus on simulation of solidification process. Here, I will use an example to demonstrate how we can use it to predict hot cracking in aluminum alloys. As we all know, hot cracking are very common defects generated during solidification of casting and welding, and also even additive manufacturing. Hot cracking is a very complicated phenomenon. So many criteria have been developed in the past several decades to predict hot cracking susceptibility of alloys. So we can people try to avoid this kind of cracking, right? In 2015, Professor Cole from University of Wisconsin-Madison proposed a criterion to evaluate the hot cracking susceptibility. In this criterion, the cracking susceptibility index, the index was defined as the maximum of dt over dfs square root. T is the temperature and Fx is the fraction of solid. So basically from this, if this CSI, this index is higher, that means you have a longer liquid channel to feed. Then it will easily to lead cracking. But if this number is smaller, then you have a very short liquid channel. So it's very easy to fill the liquid in there. And so it will avoid cracking, okay? So in Professor Cole's paper in 2015, he provided a very detailed derivation to prove that this is a good index to predict cracking. But I do not have time to go through all the details. You are welcome to read the paper here, at least here, okay? Okay, so this index is very simple and effective. So in here, I just want to use this criterion. We can calculate the CSI given any alloy composition. So in this example, we use high throughput calculation to calculate the CSI for several hundreds of alloy compositions in this ternary system. Alumina, copper, and magnesium in alumina corner, okay? So copper varies from 0 to 5%, and magnesium also vary from 0 to 5%. As you can see, we predict the most vulnerable composition region is here. Basically, it's around 2 to 3% of copper and like 1 to 2% of magnesium. So this prediction agree with the experimental observation very well, actually, okay? And now we're trying to use this index to predict hot cracking susceptibility in multi-component alloy system, okay? So by far, I have shown some application examples for the first and second generation of CARFAT simulation tools. As you can see, they have played a very important role in ICME in the sense that they can help us to optimize alloy composition and also processing conditions to achieve the desired microstructure and then the mechanical properties and also performance. One major advantage of CARFAT method is that it can be applied to multi-component system. Therefore, we can use it to solve practical problems. Although the first and the second generation CARFAT simulation tools are very successful, but one thing they cannot do well is to simulate microstructure evolution. For example, this beautiful picture shown here, this is simulated by phase field simulation. It cannot be simulated by the first and the second generation CARFAT simulation tools, okay? So the next part of my talk is to talk about extent Pandex software to microstructure modeling, okay? So basically in recent years, people started to develop third generation CARFAT software due to the desire to of integrating thermodynamic calculation with microstructure modeling. For example, phase field simulation, finite element method, and cloud calculation, and so on and so forth. And for this type of simulation, it needs massive calculation, basically millions of thermodynamic calculation during the simulation of microstructure evolution. So it's really very challenging, okay? Here, I just want to use phase field simulation as an example. So if you type in phase field modeling in Google, immediately you will get like 260 million results pop out, okay? So as you can see how hot this area is. Basically, phase field simulation can be used to understand like solidification, spinodal decomposition, precipitation, green growth, and so on and so forth. So it's there is no doubt this is important tools for SEME, right? However, although it's very important, but as I know, phase field method hasn't been widely used for industry applications. The reason is we can see there are 3 gaps here. Basically, the first one is multi-component alloys, how you deal with multi-component alloys. As I said, phase field simulation require millions of simulations so it's really time consuming. In multi-component system, it's not practical, okay? And then the other problem is because there are many, many different applications. So people have different models to describe different phenomena. And how you can plug in different people's models into the software platform. This is another gap. And also user-friendly. A lot of phase field code, it can be only played by people who can do programming. So for people who do not know programming, then they cannot use this kind of tools. So, and with this situation, in the past, traditional method usually do phase simulation by like curve fitting and of Gibbs energy, pseudo binary and ternary, and extrapolation from key binary and ternary and so on to reduce the simulation requirement. So, but this is not really, it cannot really handle the real multi-component alloys, okay? So because of this problem, so we have been working on this issue for the past couple of years. And this year we released a new module, phase field. And hopefully it can solve this kind of issue. And we want to fill the gaps, 3 gaps for industry application, okay? Some highlights of phase field model. So in this module, we directly coupled CARFAT calculation with phase field modeling. No curve fitting is needed, okay? And we can directly apply to multi-component alloys. We do not need to do any assumption for binary or pseudo-binary or ternary, okay? And a very key feature of this platform is that we allow users to plug in their own model. So it basically has an open architecture, okay? So if you have a model that you think that can solve your issue very well, then you can plug in your model into our platform, and then you can do the simulation for your applications. And also we develop a very user-friendly GUI, which can conveniently to do simulation for 1D, 2D, or 3D simulations. And also we can do like a high performance simulation with different computing environments. All right. So here I just give you a quick a schematic diagram which shows our design for the pan phase field platform. Okay. So as you can see, it directly integrated with CARFAT simulation to get thermodynamic input, and then it can. Currently, we have developed two models. Two models. One is for precipitation simulation, and the other one is for spinodal decomposition. But here, I want to emphasize that the key for this design is that we allow user to plug in their own model for their own applications. Okay, this is a key feature of the platform. Here, I just want to show you a few examples. Here, this one is a simulation for a 6-component refractory high entropy alloy, and it's a spinodal decomposition. For this 6-component alloy system, it takes like less than an hour using your PC. So it's very manageable, okay? The second example is a 3D precipitation simulation of a nickel-based superalloy. As you can see, the nucleation and the growth for this alloy can be clearly viewed from the microstructure evolution 3D diagram, 3D figures, okay? And if you want to see a 2D in a certain section, you can certainly do that, okay? This one, and also, as I said, the purpose is to use this module for industry application, right? So we can apply it to multi-component system. In this case, we apply it to nickel-based superalloy U720, which is a multi-component system. Again, as you can see, the particle nucleate, grow, and coarsening, and so on and so forth. And also we can consider it's not limited to isothermal aging. We can consider like a 2-step aging, for example, and you can see the first aging step, you have nucleate growth. And then when you drop the temperature, some new nuclei will form and grow. So you can see clearly the secondary and the tertiary gamma prime, okay? So that's the phase field module. In addition to the Pandex software with all 6 modules, we also developed a PanPython SDK. So this SDK is specially designed for convenient linkage of Pandex software with any other external material models, okay? So then it can be facilitate material designs and parallel computing and so on and so forth, okay? This is basically another extension of the software. And for example, we can use PanPython SDK for parallel high throughput calculation. As I already demonstrated, high throughput calculation is a built-in functionality of Pandex software, right? Which allows user to perform several thousands of calculation by a simple setting. However, if you are very ambitious, you want to perform like 2,000 millions calculation, then it's going to be very challenging. It still takes time, right? But if you use PanPython SDK, then it will allow you to do parallel high throughput calculation. And then you can use multiple computers at the same time, which can significantly enhance the high throughput calculation capability, okay? And then after the calculation, Python can also perform post-processing for the massive data, okay? Then therefore we can perform data analysis. And here is an example. Basically in this example, as a user, you can define, let's say, I want B2 phase varies in the range from 50 to 88%. And the BCC phase vary from 0 to 50%. And then you, when you vary this fraction, you can see from the left bottom figure how the composition of each element will change. So it basically tells you when your composition vary in this composition range, you will attain this kind of phase fraction. And the left and the right bottom figure, it also tells you how each element will affect the fraction of each phase. Basically, the positive number means the element will promote the formation of this phase. And then the negative number that, of course, then it's not good for this phase formation, all right? And in this example, it basically analyzes the data from high throughput calculation of a precipitation simulation. And the left figure shows the maximum yield strength varies with the composition of silicon content and magnesium content. And then the right figure shows you the composition range for magnesium and silicon when you can reach a yield strength higher than 240 megapart, okay? So this kind of analysis is very helpful to see immediately how you can optimize your composition, okay? All right, this is my last slide. Basically want to summarize what I have been talking about. Codified approach and simulation tools have evolved from first generation for phase diagram calculation to second generation for kinetic simulation, but it's a mean field approach, right? And then now it's to third generation for microstructure evolution modeling, okay? And codified modeling tools are very important for ICME applications, and currently it is used by many ICME practitioners for alloy design and processing optimization. The capability of codified modeling tools can be further extended by using Python SDK, okay? And for Pandex software developed at CompuTherm, it adopts a module design, so its capability can be extended further, okay? Even though now we have 6 modules already, we can further extend its capability in the future, all right? And lastly, but very importantly, I want to mention that initially Pandex software was developed by the support of Air Force Research Lab through SBR project. So I really want to thank Air Force Research Lab for the supporting of this program. That's all for my talk today, and I'll be happy to answer any questions you may have, okay?
Awesome, thank you very much. And I encourage everyone to go visit CompuTherm.com, reach out with any questions or follow up afterwards. We do have some time for some questions in the time we have left. So if you do have a question you'd like to ask, please submit it via the Q&A functionality there on the toolbar, and we can facilitate that. And Fan, thank you very much for the presentation. Thanks for mentioning that this is brought to us by the U.S. Air Force. Can you talk a little bit about the benefits that this particular software has versus other things that are on the marketplace? What its particular what does it do better, I guess? Well,
actually,
than some of the other ones that are out there.
Sure. Well, I think this when we develop software, there are already some software package available in the market, but we found some issues with the existing software, so that's why we decided to develop our own software. So when we start to develop this software, computer science is more advanced and everything is more ready. So I think there are a few key features of our software. One is the calculation engine is really very stable. So it adopts a global optimization algorithm. So the software always find the most stable phase equilibrium. So that's one of the major feature for the software. And the other feature is the software is very user-friendly. So after a couple of days of training, you can learn the software and become the expert. And the third advanced feature I want to mention is the modular design, already mentioned in my talk, right? Because the modular design, users learn one software package. Basically, the user interface is very similar at the different modules. And then in the one software, you can perform different type of simulations, like from the first sentence reason for phase diagrams to kinetic simulation. And now even you can perform phase field simulation, and all share one user-friendly interface. So it's very convenient for the user to learn the software package, and then you can perform different type of simulations from thermodynamics all the way to microstructure modeling. Okay.
Very good.
Yeah. Mm-hmm.
Yeah. Very good. Thank you. Someone wanted to know what the benefits were versus some of the other softwares available on the marketplace. So thank you very much for that. Now we do have some technical questions, so hopefully we can handle these in some of the time that we have left. So can the HTP calculation be done using a command prompt without GUI, and how long does it take to run those calculations?
Yes, the answer is yes. You can do high throughput calculations through, you don't have to go through GUI. You can do through command line. And the calculation is pretty quick. Well, if you like to try, you can download a demo version from our website, and then you can try the high throughput calculation. You can see it just go quick, very quick. Okay, so if you want, you just do several hundreds of calculations. You can finish it probably in 5 to 10 minutes with your PC. Okay, it's very quick.
Very good. Is there any way to estimate how accurate the results of an equilibrium calculations are given the alloy composition and the chosen database? Sometimes it seems more obvious than other times, but is there a way to estimate how accurate the results are going to be of the equilibrium calculation?
Well, this is a very good question, because this is basically based on the approach of CARFAT method. So CARFAT method, one key factor is the database. So we developed the thermodynamic database, and also now we develop other databases as well. We developed this database based on the available experimental data, and also sometimes we use first principle calculated data. So surely in some of the composition regions, probably the database is more accurate than it in the other composition region. So I know this question is very advanced question, I would say. So sometimes it depends on how the database is reliable in the composition region you are working on. One thing you can see is you can see how many binaries and the ternaries that are fully modeled in the composition region you are working on. If all the binaries and the ternaries that are fully modeled, then I would say the calculation would be quite accurate. But if you use the database in the composition region that some of the binaries or ternaries are not fully modeled, then probably it's not as reliable as in the other composition region. Okay.
And I'll make sure that these the folks who are asking the questions are passed along to see if there's any follow-up offline afterwards, in case there's more specifics that we need to get into, so you guys can certainly connect afterwards.
Sure.
Does the two questions here? I'm going to combine them. Do you have the capability of modeling sintering, and can you predict the strengths of high entropy alloys?
Well, sintering, right now I don't have a definite answer to your question, but I think at least you can use our software to understand what's going on during the process, okay? But probably we don't have a button you press and they say, okay, do the sintering for me. We don't have that. but through the simulation of a different property, you probably can understand some of the phenomena. For high entropy alloy strengths, yes, we have the capability. We can do the simulation using pan precipitation module, but we do need to develop some kinetic parameter database. But if you are interested, we can work together to develop that kinetic parameter database, okay?
Yeah, well, like I said, we'll make sure we connect these folks with you offline. 2 more questions in the time that we have. The first one is, can the software calculate mechanical properties, temperature and phase dependent of a given material and a given process, whether heat treatment or welding?
Yes, as I already demonstrated, we can do some, like a yield strength simulation, some kind of kinetic, some type of mechanical properties. It's probably not all of them, but like yield strength, hardness, and so on and so forth. We can do the simulation using a pan precipitation module. But I'm not sure what mechanical properties you are interested, but again, you're welcome to contact us and yep. we'll have more discussion.
Finally, one more, along with the software, do you offer both the software as well as consulting services? It sounds like we have to connect with some folks offline. So do you offer those kinds of services as well?
Yes, we do. So we offer both. We offer, certainly if you use our software, right, we provide support of the software
exactly.
using. That's certainly. But if you say, okay, I don't have the personnel who can do like computer simulation, can you do the simulation for us? We do, okay? We can provide consulting service to you, okay?
Excellent. Well, I think that is all the time we have for questions. I do want to thank everyone for their participation today. Thank you very much, Stefan. Thank you very much for CompuTherm for your membership. And thank you for the plug for LIFT membership. I encourage everyone that's on the call to contact us, learn a little bit more about LIFT, contact CompuTherm, learn a little bit more about their business and their software and how they might be able to help you going forward. Stay tuned for additional webinars in the future. Our Liftoff series will slow down a little bit in the summertime here as we head into June, July, and August, but we will still have a few coming up in the next few months. So stay tuned to your emails and your websites for that. In the meantime, you can revisit this website or this webinar on our website later on this afternoon and share it with folks who may not have been able to participate today. So again, thank you to CompuTherm, thank you to Fan, and thank you to everyone for participating today, and hope everyone has a great rest of the day.
Thank you, Jill, and thank you, everyone. Bye-bye.